Okay, great. Hello, everybody. This is Chemistry 2330, Introduction to Organic Chemistry at Texas State. I am going to do my administration first, and then we'll get into the slides for our next section of goals that we're doing. Okay, so for administration, like I said, there was, somebody noticed that one of the videos online was a duplicate. I have since fixed that. It should be on your playlist correctly. It might not be in the exact right order anymore because it only does it by date. It doesn't let me sort by, you know, title or logical order or anything like that. So it's going to be a little out of place, but it should be there and it should be correct now. I have also, if you look on the track site, I have put in all the assignments and when they're due. You do not submit them to Canvas, but Canvas will tell you when things are due and ping you. Does anybody else have no audio? Do I have audio? I have audio on my side. My microphone is working. Anybody else having audio issues? Can anybody hear me? Most people can hear me. Okay, so I'm sorry, but I think that we are, it might just be you. Try unmuting. Every once in a while, I end up muting my computer and it actually mutes the entire system. So, okay, I believe everybody's been let in out of the waiting room. Okay. So back to Canvas. Canvas now has when all the different homeworks are due, as well as the exams. The only thing that's not on there is group activities, and we'll start group activities next week. So I'll put those on there as soon as I figure out which ones I want to do. I definitely want to do one for chirality, and I definitely want to do one for functional groups. So I'll have those, I'll add those as I get those kind of worked out for this particular class, okay? So the new thing in Canvas is the assignments. Again, you do not submit them there, you submit on Top Hat, but it gives you an idea of when things are due. In addition to that, on the track site, I believe, it might be in the files. Yeah, it's in files. It's called Lecture and Exam Schedule. So this is basically just a PDF form of the different lectures we're going to do, which chapters we're going to hit, which days, when we're going to have exams, and when the homework is done. It's basically the same thing as what's on the assignments, but it's in a PDF form that you can just, you don't have to be online to look at, so you can use that as well. Okay, so the next most important thing about our class is what is due this week. The only thing due this week is that Chapter 1 homework on Friday, but you have to go ahead and get into Top Hat. I sent in a couple more invitations if you lost it in your email to join Top Hat. And I believe the paywall has been fixed such that you are only paying for access and testing. And so that way there should not be a homework component. If you did accidentally have to buy the homework component, go ahead and email the support at Top Hat, and they should refund that for you. I've fixed that all on the Top Hat side, so you should get all of that money back if you did accidentally purchase that. All right, so again, expect an email on Monday with our new Zoom meeting for that week. So every Monday morning, I will send out an email with the new Zoom link for that. Some people seem to be losing it in their email. So what I might start doing is also posting it on our Canvas site so that you can properly link it from there as well. Okay, that is all I have for administration. Does anybody have any questions about the class so far? Having a difficulty to getting the book or the lab book? I know the bookstore should have the lab book, and that should be available.
Professor, I have a question about the lab book for people who registered on the online section.
Mm-hmm.
Do we have also to buy the same book?
You do need to buy the same book because that has all the pre-lab procedures. The only difference is that you don't have, you can actually, you'll not be handing in the physical copy. So what you'll have to do is take a scan or a picture of your, the pre-lab and your observations and upload those to Canvas.
And to Canvas, not onto the tracks.
Not tracks, yeah. All of our submissions will be to Canvas. We have to switch over to Canvas this year.
And we can upload a picture. It doesn't have to be scanning.
Correct.
Okay, thank you.
So you can upload a picture or a scan. There's a bunch of different apps that do it, you know, so whichever works for you, that's fine. The important part is the information you've written down on there.
Okay, and how about the quizzes?
The quizzes are going to be held by Zoom. If it's not in person, they will be, you'll have a pre-lab that's going to be pre-recorded. And then you'll also have Zoom proctored quizzes for each lab.
Okay.
And we'll get more information on that in about a week when we'll start laying out all the examples next week, because we don't actually start till the week of the 14th.
Okay, thank you, doctor.
There's a note in there about part 5 being an actual part 4 again. Yeah, that should be fixed now. I should have deleted the part 5 that was the duplicate, and you should have the new part 5 on there now. It's not going to be in the exact same place. It's down below. All right, great. Lots of questions answered there. If the lab books, if we don't have lab books next week, what I can do is I can actually upload those pages for the lab 1. Actually, the lab 1 is just safety anyway, so we'll have, we can upload the lab 1 safety thing that, until everybody has a book. I just can't upload the whole thing. Part 2.2 is chapter 2 as well. Okay, I'll look into that one as well. Okay, so that's administration for now. Any more questions? Go ahead. I have that Zoom chat here. I'm watching your Zoom chats for questions and such. 2 part 2s in chapter 2. I'll double check that. Part 2. Okay. They look different here. There's 2 part 3. Okay, so I'll look into that. All right, so let's continue on with chapter 1, and let's get back to where we were on our slides. And we were talking about how to do the Lewis dot structures, and that when we build those Lewis dot structures, that gives us a valid place to start, okay? As far as, okay, we put the atom that needs the most bonding in the middle, and we start building on it until all of our main group atoms have 8 electrons around them, and then we know we have a good valid structure if we have to make a second bond or a third bond to make sure we have all those electrons available to us. Okay, so now that we've made a Lewis dot structure, the next step is for us to actually calculate the formal charge on each atom in the system to see if the entire molecule has a charge, or if we have charges on 2 different atoms. So that's the next thing we're going to learn today. And so I'm going to start sharing my screen. Come on, you can do it. There it is. All right. So I'm going to go ahead and move my gallery mode up here so that I can see if anybody's cat invades our class. Okay, so now what we're going to do is we're going to look at, now that we've been able to draw a whole bunch of those bonds around things, and we know how to count those electrons, that each line counts for 2 electrons, and we want to have most of the time 8 electrons around the thing. Now let's look at what that formal charge on each and every atom in a molecule or a polyatomic ion. What this does is this helps us to understand, even if we have the right number of electrons, we might have the incorrect number of electrons to balance the charge of the nucleus. That means that we could have a positive charge if we don't have enough electrons, or a negative charge. And so we need to know this because that's important for, number one, how they react and what the entire net charge is on the molecule. So the way we do that is we have to first draw our Lewis dot structure, which is why we did that first. And then we have to think about all the shared, which are the non-bonded, unshared electrons, which are like lone pairs that aren't being bonded to other things. And we have to think about all the bonded electrons. We can only count half of those bonded electrons because it takes 2 electrons to make a bond. And so that we can only say that one of those electrons is on the outside of that other atom 100% of the time. So we have to take into account non-bonded electrons and bonded electrons, okay? The next most important thing we have to do is remember how many valence electrons the neutral atom had to begin with. So that goes to that A number on the top of the group. So like carbon is an A4, which means it has 4 valence electrons in its neutral unbonded state, okay? So now we have to do a little bit of algebra, but we have a nice little equation here that I like to show is the one right here, where we have the formal charge is equal to the valence electrons of the unbonded neutral atom. So this we can equate to where it is on the periodic table. So like boron is a 3A, carbon is a 4A, nitrogen's a 5A. So carbon has 4 electrons, nitrogen has 5 electrons, oxygen has 6 electrons. So that's where we get the number from for this number here. Now the EP right here is the unshared electrons. Okay, so those are like the lone pairs that we have. So those are the unshared electrons. And we get to use all of those because those are unshared and sitting on the atom. But we can only use half of the bonded electrons, okay? Because because they're being shared, half of the time it's spinning at the other atom and half the time it's spinning at the atom of choice. So we have to use only half of those. So that's our equation is, and what we're gonna do on the next slide is kind of use it a little bit. So I have 3 examples I wanna use to do formal charge. And the first step in our formal charge is to draw a Lewis dot structure. So I'm gonna do these 3 examples here at the bottom. So let's start first with the carbonate ion, which is a carbon with a double bond to oxygen. And then O, electron, 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 because we have a negative charge here. And O, electron, 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 a negative charge here. Okay, so that's how the ion looks right there. But what we're going to do is we're actually going to calculate the formal charge for each of the atoms and see whether or not they have more charges than we can see just by looking at it as an ion. Okay, so if we look at the carbon here, so a formal charge is equal to the valence electrons minus the unbonded electron pairs plus 1/2 of the bonding electrons. Okay, so notice this whole thing is in brackets. So we want to do this operation first, and then we're going to subtract it from the valence electrons we start. So carbon being in a group 4A, we know it's going to have 4 electrons that it brings to the party. Okay. Okay. Now, if we look at carbon, there are no lone pairs on carbon here. So that means we have 0 non-bonding electrons. Okay. But we have to add 1/2 of our bonding electrons. Now, each of these lines is 2 electrons, so that's 1, 2, 3, 4, 5, 6, 7, 8. It has 8 bonding electrons, so 1/2 of 8 is going to be what we're going to include in our equation. Okay. So 1/2 of 8 is equal to 4 plus 0 inside the brackets, minus 4 is equal to, and so that means 4 minus 4 is going to be equal to 0. That means the formal charge on oxygen on this carbonate ion is 0. The entire molecule itself, the ion has 2 negative charges, but carbon itself has 0 formal charge. okay? So let's do it for the two different types of oxygen atoms we have. So we have two different types of oxygen atoms. We have this oxygen atom that has a double bond to carbon, and then we also have this oxygen atom that has a single bond to carbon, okay? Now these two look alike, so we're gonna assume whatever we calculate for the one is gonna look like the other. So I'm only gonna do these two different types of oxygens, okay? So we're going to, using our same equation, but we have to put different numbers in now, okay? So let's do this one first, right here. So we have oxygen. Oxygen is group 6A, which means it has 6 valence electrons. So that's what we need to start with there first. And then we have, if we look at this, we have 1, 2, 3, 4 electron pairs or lone pair electrons. Those electrons are not bonding, so those count as those non-bonding EP electrons, right? Plus 1/2 of, we have 1, 2, 3, 4 electrons in those two bonds. So 1/2 of 4 electrons. Oh, that's it. Okay, so 1/2 of 4 is 2, plus 4 minus 6 here, which means the formal charge on this oxygen is 6 minus 6, which is equal to 0. So the formal charge on this type of oxygen in our system is 0. And so that also does not contribute to the overall charge of the molecule. Okay. So now let's do the last one. And luckily we get to use some of the same numbers. Right here, we're going to just do this last one right here. Oxygen again brought 6 electrons to the table. It has 1, 2, 3, 4, 5, 6 electrons that are non-bonding. Oops, 6 that are non-bonding, plus 1/2. Oops, I drew an extra electron there. It only had 6 electrons. All right, so it has 1, 2, 3, 4, 5 electrons there. No, it's got 6. I'm sorry, I was right. 6 electrons there. And then we have 1/2 of 2 electrons here, because there's 2 electrons in that. So that gives us 6 plus 1 in the brackets. So we have 6 minus 7 is equal to minus 1. Okay. So why did I add that extra electron? Because we wanted 8 electrons around our oxygen atom to make sure that it met its octet. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons around that oxygen. That extra electron gave us our -1 charge. Okay, so now when we do that calculation on this side here, we're going to get a negative charge. So our net charge on the entire species is going to be -2. Okay, so I'm going to do this calculation one more time on the acetate ion, and then I want you to do it again at home on the acetone. Okay, so I'm going to erase this structure, and we're going to draw an acetate ion. The acetate ion we use a lot because it is, number one, it's very easy to make. We take acetic acid or vinegar and we take a proton off it. And so that's why we use it a lot. And it's really easy to make and really easy to use. All right. So let's first draw our acetate ion here. And so our acetate ion, if we draw our Lewis dot structure to it, we have C, H, 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 and we'll learn this functional group in just a little bit. Let's see, we have to have 1, 2, 3, 4, 5, 6, 7, 8. So this carbon's happy. This carbon right here has 1, 2, 3, 4, 5, 6, 7, 8. That's happy. This oxygen has 1, 2, 3, 4. So we need to add 4 more electrons to make it have 8 electrons. And this has 2 electrons. So let's go 3, 4, 5, 6, 7, 8. All right. So every atom now, all the larger atoms have 8 electrons, and the hydrogens have 2 electrons. So we now have a Lewis dot structure, but we still need to calculate our formal charge. Okay. So what we have in this is we have our carbon in the middle. That's one thing we're going to calculate formal charge on. And then we have two different oxygens. We have this oxygen here and this oxygen here. They're different because one of them's bonded twice and one of them's bonded once. So we need to calculate all three. So let's start with our carbon. Let's do our carbon here. And we have 4 valence electrons because of where it is, minus. We have no non-bonded electrons. So we have 0 here, plus 1/2 of 1, 2 for this bond, 1, 2 for this bond, 1, 2, and 1, 2. So a total of 8 electrons that are bonding, which gives us 4 minus 4, which is equal to 0. The formal charge on carbon is 0. Okay. Let's move to this oxygen here. So we're going to do our oxygen, and I'm going to do OX to make sure we don't think it's a 0. And the oxygen brought 6 valence electrons to the party, right here, minus we have 1, 2, 3, 4 non-bonding electrons. And we have 1, 2, 3, 4 bonding electrons. So we got plus 1/2 of those other 4 electrons. So that makes 2 plus 4. So that makes 6 minus 6 is equal to 0. So the oxygen here on top has a formal charge of 0, and the carbon has a formal charge of 0, but we know it's an ion because we called it an ion. So let's calculate that last oxygen and see where it is. Okay. So if we look at this last oxygen here, we're going to start with 6 electrons because of where it is on the periodic table, minus, let's see, 1, 2. It only has 2 bonding electrons, but it has 1, 2, 3, 4, 5, 6 of the non-bonding electrons, plus 1/2 of 2. We only have the 2 bonding electrons. So that's 6 plus 1 minus 6. So that's 6 minus 7, which means the formal charge is minus 1. Okay, so we have now found out where the charge is on our ion, our acetate ion species. It's on the oxygen that's only singly bonded to 1 carbon. Okay, does everybody understand formal charge? Okay. Any questions about formal charge? All right.
Dr. J.
Yeah.
So I guess the hardest part about it is just setting up the Lewis dot structure, because then once you go from there, it's just looking at the periodic table, right?
Right. And by doing the steps in the Lewis dot structure where you take the thing with the most bonds, try to put that in the middle, like carbon only has 4 electrons, and then we build out, and then we make sure each atom has either 8 electrons for the oxygens and the carbons and the nitrogens, or 2 electrons for hydrogens, then that's why we ended up with these, what seemed like a lot of electrons here. That extra electron we needed to make that octet is why it has charge. So make sure you have your 8 electrons and then calculate your formal charge. Okay?
Yes, sir.
Okay. So let's move on to the next thing. Okay. So the next concept we're going to talk about that involves these Lewis dot structures is what we call resonance. Now, resonance is when you can draw 2 or more equivalent Lewis dot structures and there's no chemical difference between them, okay? Which means that you could say the electrons would be on one atom or the electrons can be on a different atom nearby, okay? So the key with resonance is that you can draw more than one valid electronic structure and they might all be true, okay? There might be a favored one or an unfavored one, but they could all be true. Now, another key about these resonance structures is the only difference. They're all connected the exact same way. The only difference is where the electrons are, okay? So that means when we have an electron structure, we can actually move electrons from one location to another using what we call a double-headed arrow. The 2 barbs means 2 electrons. We are going to do a thing called a radical where we only move 1 electron and then we only have 1 barb. So if you see 2 barbs on an arrow, that means 2 electrons are moving. Okay. So now, because we can have more than one structure that looks valid as a Lewis dot structure, and we can move electrons from one to the other without breaking any bonds, we're just moving electrons, we call this molecular ion a hybrid because it really doesn't exist in any one structure. It exists as some structure in between. So let's look into that a little more detail and see if we can't understand. Okay. So a great example of this is what we call the carbonate ion. Remember, we draw the Lewis dot structure for the carbonic acid before, but now we're going to look at this as the ability to move the electrons around and form different real Lewis dot structures. And again, none of these Lewis dot structures are wrong. They're all correct. And so the reality of it is somewhere in between. So let's look at our first Lewis dot structure here. Let's double check it and make sure it's correct here. We have a total of 4 electrons here, so that oxygen has 8 electrons around it. This has 6 and 2, so this one has 8 electrons around it. And so that has 8 electrons around it, that has 8 electrons around it, So all of these atoms have 8 electrons around them, so this is a valid Lewis dot structure. Okay. So where resonance comes in is, okay, why is this the only oxygen with a double bond? Why can't this oxygen be double bonded? Or why can't this oxygen be double bonded? Well, it can. And all we have to do to make that happen is to take these electrons, move them here, and move these electrons out, and we end up with this valid Lewis dot structure. Okay? All we did was we didn't break a connection between a carbon and an oxygen. We didn't add a new connection between 2 oxygens. All we did was move an electron around, changed which atom had that second bond. Okay? Now, why can't this one up here have the double bond? Well, there's no reason it can't. And if we looked at a resonance structure by moving these electrons in to form the double bond and these electrons out to form the double bond, we'll end up with this resonance structure. Okay. This Lewis dot structure. Okay. Now notice this is a double arrow in between here. Okay. So when we draw chemical structures, we have to pay attention to the different symbols we use. Okay. So when we have these double arrows that are curved with these 2 carbs on here, that means 2 electrons are moving to that location. Okay. When we have this double arrow in between 2 structures, that's symbolizing resonance. Okay, that's saying that it can move back and forth, and the only thing that's moving is electrons, our electrons. Okay, so that double-headed arrow. We will have different arrows like this. That means something else. So I wanted to draw attention to the fact that this double arrow between 2 Lewis dot structures means there's resonance. All right, questions on that? Okay, so that's the concept of resonance, that we can draw multiple different valid Lewis dot structures using the same materials without changing the overall charge or the overall structure of the compound or ion. Okay, so again, the curved arrow with 1 barb on it is moving 1 electron. The curved arrow with 2 barbs on it is moving 2 electrons. Okay. Now, one of the rules of resonance is you can only move atoms. You can only move electrons in resonance structures, and you can only move them to between 2 atoms or from a bond onto an atom. So they have to be. You can't jump electrons across an atom from one oxygen to the other. Notice those electrons went to the carbon, and then the ones that were bonded to the carbon went to the oxygen. They were connected. Okay. So this is what we call electron pushing. Okay. And we use these curved arrows to show you where things are going. When we start talking about how things work and mechanisms and other things like that, we're going to show that electrons are going to move in to create a new bond. Electrons are going to move out to break a more complex bond. We're going to see this again and again and again. Okay, so some other rules of resonance is that all acceptable resonance contributors must have the same number of electrons. You can't gain or lose electrons. Can't do it. Number two, you must obey the rules of covalent bonding. Hydrogens only have 2 electrons, never more. Anything in the second period, which is your carbon, nitrogen, oxygen, chlorine, can only have 8 electrons in their outer shell. Occasionally, things in the third period, like sulfur and phosphorus, can have up to 12 electrons and can bond up to 6 times. Okay. So, what that means is it only differs in where the valence electrons are. Not the number, not the connections, only where those valence electrons are. So you must have the same total number of paired and unpaired electrons in each of your structures to be a true resonance contributor. So every one of the ones that you can draw that's valid will contribute to the overall resonance of the structure. Okay. So I'm going to show an example, and we just saw carbonate before on the previous slide. So what I'm going to do is I'm going to show you the resonance on the acetate ion. We use this a lot as far as how we look at the resonance. And if we draw the acetate again, we have a carbon here, oxygen, electrons here. We have oxygen here, electron, 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 electron. And remember, now that we know that this is the formal charge because it has those 7 non-bonding electrons, that we know that this is where our -1 resides. Then we have our carbon over here. Okay. Now, the first thing to think about is that, okay, let's look at this carbon over here, right here. It doesn't have any lone pairs or double bond next to it. So we really don't care. That carbon is not going to change, okay? So we don't have to worry about where to push electrons on that carbon. We do have to worry about it on the 2 other ones that have double bond going to a single bond and those lone pairs available to come in. So we don't have to worry about that side of the molecule. So let's start worrying about this half of the molecule here and see if we can't make a resonance contributor that looks different from this one that's here. So I'm going to draw that double-sided arrow to show that we have a resonance structure here. And I'm going to draw the part of it that doesn't change. So we'll have at least the same connections here. The only difference is electrons have moved, okay? So let's go back to our original one and let's start pushing some electrons. So if we pushed these electrons in here, that means we would have 10 electrons around this carbon, which means that it wants to get rid of 2 electrons somehow. So it can actually push these 2 electrons up to this side, okay? So notice the only thing that's moving is electrons. So if we do that, that'll end up with our double bond here, and we still have 2 lone pairs on this carbon. But we had 2 lone pairs on this carbon here, but we added another lone pair, so we're going to end up with 6 electrons on this carbon. Okay, so this is now a valid Lewis-Dot structure, but it's different than the one on the left here. So that's how resonance works. The fact that all we did was move electrons, we didn't move the position of atoms, we only moved electrons around. That is resonance. Okay. Now, if we did our formal charge calculation, this would be our -1 oxygen on this side, but this would be our -1 on this side. Okay. Questions about how we do resonance? All the atoms are connected the same way. We just move electrons. We move electrons with those curved double-barbed arrows, and we demonstrate resonance with a double-sided arrow. All right. Let's see. Okay, so that's how we get to those useful Lewis dot structures. I can draw any little thing around, and you could probably figure it out, but it'd take you some time. So what I'd like to do now is introduce you to the concept of functional groups and give you some, what they look like, and so you get kind of familiar with them. This might be one of those things where you can draw the general structure and do a flashcard and just make sure you know the different functional groups. We're going to be using all of these functional groups for the rest of the semester, so it wouldn't be a bad thing to use some flashcards and learn all these classes of compounds. Okay. So what we mean by functional group is that it is the actual part of the atom that does like something, okay? So it's the one that actually has functionality and will actually do the chemical reaction, okay? So functional groups are important for three reasons. Number one, they divide the organic compounds into different classes. So an alcohol reacts differently than an alkyl halide, reacts differently than a carboxylic acid. So it gives us different classes to play with, okay? The other thing the functional group does is it gives us the sites at which certain reactions happen. Alcohols react a certain way and do a certain thing. Alkyl halides react a certain way and do a certain thing. And carboxylic acids react in a bunch of different ways, okay? So those functional groups tell us where the chemistry happens, okay? The last thing it does is it also helps us subdivide all our organic compounds such that we can name. And so there's an entire class that will, of naming structures called nomenclature, and we'll get into that as well. I have even a group activity. All right. So the first functionality we want to talk about is the alcohol. Alcohol just means it is an oxygen with a hydrogen on it that's bonded to carbon, okay? So, and it's typically bonded to a tetrahedral carbon. So if we look at our structure here, oops, if we look at the structure here, we have a single bond to carbon and a single bond to hydrogen. If that oxygen's bonded to two carbons, then it's a different group. So it must be bonded to a carbon and a hydrogen. Now, if we look at the skeletal structure, we would draw it like this, assuming that this is a carbon and it has hydrogens on it, and assuming this has hydrogens on it as well. So the skeletal structure would look like this. Notice whenever we draw the skeletal structure, if it's not carbon or hydrogen, we specifically label it. And that makes it easy to identify the functional group. All right, the next functional group we're going to talk about is the amine. And it's similar to the alcohol, except that instead of an oxygen, we have a nitrogen. Now, nitrogens are a little more complex because nitrogens bring, oxygen only had 6 electrons that were valence electrons, which means it can only bond twice. So that means we only got 1 structure out. Amines can't have 5 valence electrons, which means it wants to bond 3 times. And that gives rise to a level of complexity. For example, if you have a nitrogen that's just bonded to 3 hydrogens, we have a special name for that, it's ammonia. Technically, it's not an organic compound because it doesn't contain carbon. Okay, but if you bond 1 carbon to your nitrogen here, we have what we call a primary amine, meaning we have 1 carbon bonded to a nitrogen, and it's a primary amine. Notice it still has 2 hydrogens on it, okay? And these 2 hydrogens here can do chemistry. So it's important to know that you have a primary amine. Now, if you're bonded to 2 carbons, then we call it a secondary amine. So your nitrogen has 1 carbon on it here and 1 carbon on it here, but it still has that last hydrogen right here. And that tells us that we have, again, reactivity at that hydrogen, but it's bonded to 2 carbons. And then the last type is called the tertiary amine, or the trifunctional amine. So there's 3 different carbons on here, And notice that there are no hydrogens on here because the last little bit of this, there's a lone pair, which is that left over from those 5 electrons that came to the party with, and we're allowed to, so this one has no more hydrogen to react. And these react a little bit differently than the other two. Okay. So 1 carbon bonded to the nitrogen, it's a primary, 2 carbons, secondary, 3 carbons, tertiary. Now, you can actually put a 4th carbon on here if you make that nitrogen positively charged. Okay, and we'll talk about those in another chapter. But that's just the basic idea of amines. Okay, the next functional group actually has probably the most diversity in it. It's the things that involve the carbonyl. So a carbonyl is when you have a carbon double bonded to an oxygen. Okay. So this gives rise to actually 4 different functional groups, and well, more than 4 functional groups. So, so the most basic would be something like this right here, where we have an R group, can be any long chain, can be a short chain, can be anything. But the idea is that this is the functional part right here is the carbonyl and a hydrogen. So if you have a carbonyl bonded to a carbon and a hydrogen, it's called an aldehyde. Okay, so it's an aldehyde. And then there's even a simpler version where it's bonded to 2 hydrogens called a formaldehyde. We'll talk about that. The next thing is if we have 2 R groups bonded to a carbonyl, that is now what we call a ketone. And ketones are actually used a lot as fragrances and odors that we'll find in perfumes and you know, body washes and whatever, is that this has a nice sweet flavor to it. And so that is the general structure of this aldehyde. Has a carbon and a hydrogen, or 2 hydrogen. A ketone has 2 carbons bonded to that carbon. So these have specific chemistry associated with the fact that this right here is a polar bond. Okay. We have a whole chapter on all of the cool reactivity of these compounds. All right. The next functional group that uses the carbonyl is called the carboxylic acid. In its simplest form, it is basically a carbonyl right here, and then it's bonded to an OH on one side and an R on the other. So any kind of alkyl group, which is denoted, any alkyl group can be an R, and it has an OH on the other side. So see, that's different than the aldehyde of a ketone, because the aldehyde has an R and an H, and the ketone has an R and an R. So this is different. And it has that OH there, is a recognizable thing. And this is really interesting because that makes this hydrogen able to be pulled off very easily. Okay, so that's the carboxylic acid group. And there's many derivatives of the carboxylic acid group by changing out this OH. And we have a whole chapter on how to take this basic group here and change it into a variety of other functional groups. But they're all based on the carboxylic acid group. Okay, questions about those functional groups. Those are the first functional groups we need to make sure we know because we're going to be using them in the next few chapters.
Can you just go over again real quickly the difference between aldehydes and ketones? It's
Correct.
just 2 R groups and 1 R group?
Yes. Yeah, so if you think about it, if you have a carbonyl with a hydrogen bonded to it, aldehyde. And if you don't, if you have a carbonyl with 2 carbons on it, then it's a ketone. And if you have a carbonyl with an R group and an OH group, then you have a carboxylic acid.
Okay, that makes sense.
All right, so those are the 3 basic things that we have with the carbonyls. Okay, all right, to summarize this chapter here, valence electrons do all the bonding. Okay, those are those outermost shell of electrons. That's where we're going to see the lone pairs that are helping to control our structure. That's going to be all the electrons that are going to do the bonding. We use Lewis dot structures to help us use those valence electrons to do our bonding and do our bonding correctly. Once we have a valid Lewis dot structure using our 7 rules of Lewis dot structures, we can calculate formal charge and determine if that molecule we've drawn is neutral or has formal charge. Okay. So if we have a Lewis dot structure and the formal charge, we can actually then look to see if we have different resonance formations that we can make from it. And when we look at the different ways to bond, different ways in which you can bond different atoms together, that different ways we bond atoms together gives rise to different functional groups. And those different functional groups have different names, different reactivities, and different reactions associated with them. Okay? So that is the end of this part 2, chapter 1, goal 2. All right. Any questions on that so far? Okay. All right. Then I'm going to move on to I'm going to move on to goal 3. Okay. So goal 3, now that we know where the electrons that we're using are and how they bond, and now that we can make a valid structure using our Lewis dot structures and looking at our functional groups, we also need to now think about the molecular shape. We've been drawing these all in 2 dimensions so far, okay? But life is not in 2 dimensions. They have a 3rd dimension to it. Now, the way we get to those 3rd dimensions is what we call hybridization. Okay, so let's talk about hybridization and molecular shape. Okay, when we looked at these energy levels before, we saw that they had different structures, and our lowest energy level right here, our 1, had a spherical orbital, and that's all it did. Now, most of the atoms we've been dealing with are actually in this group 2 energy level, okay? And we said that it has 2 electrons can fit in its spherical orbital, and then we have a total of 3 equivalent degenerate orbitals that are at a slightly higher level, okay? So if we were to bond molecules, you would have one of them bonding to like the 1 and the 1s, and then you would have different things in the p's. And because the s is spherical and the p's are dumbbell shaped, the molecules would look different than we actually have. So somebody came up with the idea, well, you know, it can't be just bonding to an s orbital or bonding to the p orbital because the shape's wrong, okay? So we have what we call hybridization. It actually saves energy for us to raise the energy of this s orbital a little bit and lower the energy of these p orbitals a little bit and blend them together. When we do that, we stop being just a sphere and a dumbbell, and we start seeing that we have lopsided dumbbells and that we have them going in different directions. Okay. So when we do that, we have hybridizations where we can take the s orbital and 1 p orbital, and that makes us an sp hybrid, and that gives us our single bond, our sigma bond, our first bond we make. But it gives us 2 p orbitals to make pi bonds, okay? And I'll show you where we get those pi bonds. Pi bonds are bonds that are only p orbitals that are above and below the first single bond we have. Now, we don't have to blend just 1 p. We can actually put 2 p's together and leave 1 p unhybridized. And so we have 3 equivalent orbitals plus 1 more orbital that can do a different type of bonding. Or we can do what we do in carbon, which is blend all 3 orbitals together, all 3 p's together with the s, and we get 4 equivalent orbitals. When we get 4 equivalent orbitals, that means that they're all the same shape, and they're going to all point in out away from each other as far as they can, and that's where we get the tetrahedral shape of carbon. Okay, so let's talk about these hybrid orbitals, okay? We're going to talk about 3 in particular, okay? Most of the time we have what we call sp3. So if you think about it, there's 1 s there, so you're adding 1 s orbital, and there's a 3 above the p, so that means 3 p orbitals are contributing. So we have 1 s orbital plus 3 p orbitals makes 4 equal sp3 hybrid orbitals, okay? And I'll show you a little bit more about that one. So if we do sp2, that means we'll end up with 1 orbital, 2 orbitals, 3 orbitals. So we get 3 equal sp orbitals and 1 p orbital that hasn't been touched. Remember, these p orbitals are dumbbell shaped and the s orbitals were spheroidal. Huh? Question? Oh, somebody unmuted by accident. Excuse me. Okay, and if we only take one of those p orbitals, we're going to get an s and p together, which gives us 2 equal orbitals, but then at least 2 p orbitals available to do bond. Okay. So now that we have those different orbitals, the different types of orbitals actually bond in a different way. Okay, the hybrid orbitals, the sp3, the sp2, and the sp orbitals, all form what we call direct overlap bonds, and we call that a sigma bond. That's what this little symbol is. So it's a sigma bond, or it's direct overlap, meaning those electrons are shared in between those 2 atoms' nuclei. Okay, so we're sharing it directly between this nucleus and this nucleus. All right, the pi bond is the one that is parallel overlap, and that's this little symbol here, pi. And what I like to do is, if we have a carbon here and a carbon here, the one that's right in between the two is what we call that direct overlap. And what we'll see is that the p orbital here and the p orbital here forms another bond. So I like to say, well, that looks a little bit like the pi right there. So we know that that pi symbol means it's above and below that direct sigma bond. Okay, so let's talk about the shapes of molecules. Now that we know that we can blend different orbitals together in different ways, if we have 2 equivalent orbitals, we're going to have a different shape than if we had 3 equivalent orbitals, which is a different shape than if we had 4 equivalent orbitals. So we need to talk about what we call valence shell electron pair repulsion. It's a fancy name for electrons have negative charge, right? And negative charges repulse, the same charges repulse each other. So they basically want to be as far apart from each other as possible. Okay, so depending on how many regions of electron density you have, meaning a bond or a lone pair, those bonds or lone pairs are going to try to repel each other as much as possible. And when we do that, we get different 3D spatializations. Okay. So let's blow this up. So if we have 4 regions of equal electron density, and what we like to do is classically we think of that as the sp3. Because you have 1 s, 3 p's, that brings 4 together, 4 equivalent things. The best you could spread those out in 3-dimensional space is to have them 109.5 degrees apart. And we call that structure tetrahedral. So when we look at methane, that is the kind of structure we're looking at right here, where in this particular drawing, we have these atoms are in the plane of the paper. The dashed atom is sticking into the paper, and this wedge is sticking out of this. So it has, that's how we signify the 3-dimensional shape of these things. Okay? And so the farthest they can be apart from each other, and you can build a model on this, is this tetrahedral structure where each of these is 109 degrees apart from each other, and that's as much as they can do. Okay, so that's if you have sp3 hybridized orbitals and you have 4 things bonded to it. What if you have an sp3 hybridized molecule, but you only have 3 things bonded to it? How does that shape change? Well, it really electronically looks exactly the same. Because if we looked at the electrons, this electron cloud up here is 109, trying to be 109 degrees apart here. But because it's actually has those 2 electrons all to itself, it's not sharing them, it actually pushes them down a little bit more. And so the angle's a little different, and we'll get into that later. But the actual molecular shape, where the atoms are, is now what we call pyramidal. It's like a little pyramid, a little three-sided pyramid, okay? So because of these electrons above, up here pushing us down, we change the molecular geometry, but we keep the same electronic geometry. And that's sp3. Now let's look at oxygen here. Oxygen has 2 lone pairs. And so technically, if we look at the lone pairs are up here, they're trying to be at that 109 degrees. So by electronics, it's still tetrahedral. But because we don't have anything bonded to those lone pair, those 2 atoms facing down are now what we call bent. Okay? Now, they're approximately 109 degrees apart, but those 2 electron clouds are actually forcing them together. So molecularly, it's bent, but electronically, it's tetrahedral. Okay. So all of these in this tetrahedral setup have 4 equal electron domains. That means they're all sp3 hybridized. So let's go to another molecule that's now sp2 hybridized, meaning it has 3 electron domains. And when we have 3 electron domains, we end up being able to spread those out in 3D space. Turns out it's a flat triangular plane. And so we call that trigonal planar, okay? Now, I would always think that, you know, gosh, one of those would be somewhere else. No, the farthest they can get apart from each other is 120 degrees in a flat plane, okay? So whenever we see this trigonal planar structure, think sp2, because we have 3 equivalents, and then we have a p orbital left to do something else, okay? So let's look at some structures that have that. And if we have something that has 3 things bonded to it, we'll see that trigonal planar structure in our molecular shape as well, okay? So that double bond doesn't change the molecular structure. That's nice and flat. And in addition, this side here is flat. So this entire molecule, it makes a flat molecule that can, you know, it can lay flat because each side is that trigonal planar flat geometry. Okay. So if we have 3 things bonded to it, we still see that trigonal planar structure. What if we don't have 3 things bonded to it, but it's still that sp2 hybridized? Well, if we look at formaldehyde here, okay, this side of the molecule looks trigonal planar just like this stuff over here. But this side doesn't, okay? But electronically, it is trigonal planar because these lone pairs are sticking out like this. These lone pairs are all in the same plane. It still forms a planar molecule. The electronic side and the molecular side are both the same atom. Okay, so we typically think of that in the sp2 hybridized molecules. Okay? Now, then the last thing we have is what we call linear. Okay? Now, linear can be a couple different ways. One is sp hybridized, but you can also do it with sp2 hybridized. Okay? So our examples for those are, and if you have just 2 electronic domains, the furthest you can get them apart from each other is 180 degrees. Doesn't matter which direction it's pointing, it's going to be 180 degrees. And so we call them linear. 2 examples are, one example is this linear carbon dioxide. And if you notice, this part is linear here, but the electronic domains on the ends are still trigonal planar. However, in acetylene right here, this is actually sp hybridized and has that each bond here, oops, both the hydrogen bond and the carbon-carbon bond are linear, and this carbon-carbon bond and this hydrogen bond on the other side are linear. So they each have 2 domains, and they each will be in a linear configuration. Okay, so the electrons, even if there's nothing bonded to them, still help change the geometry of the molecule. All right, so let's look into changing that a little bit more. So, like I said, in something like methane right here, when you have 4 things bonded to it, it's going to try to spread out to that ideal 109.5 degrees apart. And if they're equally bonded, if they're all bonded to the same thing here, then we'll see those to be exactly 109 degrees 0.5 on all of them. Okay. Now, if we have them bonded to different things, one's bigger, one's smaller, that's going to change the angle a little bit, but it's still going to try to get to that close to that 195 degrees. Now, when we looked at the molecule that was ammonia, where we had 3 things bonded to the nitrogen, we had this lone pair. That lone pair is actually going to take up a little bit more space, and so the angle is going to be different. The angle is decreased to 107 degrees because that lone pair takes up a little more space, and it lets it be have a slightly different angle. And again, if we have 2 of these big unshared electrons, that's going to force it even more to a little bit shorter, to 104. But again, look, the electronic structure is still tetrahedral. The molecular structure has changed based on where those electrons are. Okay, so now let's look at those sp2s, okay? And again, with the sp2, we have the electronic structure of the carbon here because we're sharing 3 equivalent orbitals to make this trigonal planar system. We end up, because this oxygen is slightly bigger than these 2 hydrogens, we don't have exactly a perfect 120 degrees. This bigger group has more electron density and forces it a little more, making the 2 small groups. If they were bonded to 3 of the exact same thing, they would be much closer to 120 degrees. Okay. And therefore, that molecule, if we look at it on the side, is this flat structure. Okay. Now with ethylene, where we have it a little more symmetrically, we don't have this polar bond here, we're going to see that because carbon is larger than the hydrogen here, it does stretch it a little bit, so it's closer to 120 degrees, but not quite. And those hydrogens are smaller and are kind of squeezed together. But notice that it's completely planar from one side of the molecule to the other. And that's most commonly sp2 hybridized. Okay. So in the carbon dioxide here, we actually have the carbon itself is sp2 hybridized and the oxygens are sp2 hybridized, but they're all pulled together to give us this linear functionality. It is here, and if you look at it on end, it's completely straight, 180 degrees apart. In acetylene, the carbons here are sp hybridized to give us this linear structure. Notice we have the one direct bond here in the middle, or the sigma bond, and then we have 2 overlapping bonds that are the pi bonds, okay? Because we have the one direct and the 2 pi's, that gives us our linear structure as well. Okay, oops. Questions about those shapes? Oh, I'm finding it. All right. Okay. So now that we see that most of the molecules we'll be looking at are hybridized by blending S and P's together, let's look a little bit more on what the orbitals look like themselves before we start actually bonding. Okay, so in an sp3 orbital, we start with the idea that we had a s orbital, which is spherical, and then we have a p orbital that's dumbbell shaped. Okay, so we're going to spread that little spherical shape over one lobe of the dumbbell shape we have. So one lobe is going to get bigger and the other lobe is going to get smaller, and we'll end up with 4 equivalent materials. And so the best way to squeeze them all together is to have them get into this tetrahedral structure. Remember that our p orbitals were in x, y, and z before. Once we hybridize that, we don't need to because this is small enough to be tucked under another one, and we can get to this tetrahedral structure. Now, if we take that S and only blend it with 2 p orbitals, that means the dumbbell shape is going to be a little different, and we're still going to have a p orbital to play with. Oh, I'm sorry. Let's go show you how that fits into the tetrahedrals. So if we have 4 things bonded to it evenly, we're going to stick each of those atoms on the end of one of those sp3 hybridized orbitals. If we have only 3 bonds to it, the lone pair is now in one of those sp3 hybridized orbitals. And if we're only bonded to 2 things, each of these lone pairs is its own sp3 hybridized orbital, and each of the bonds is formed in an sp3. Oh no. All right, now let's look at the sp2s. So in the case of the sp2, notice this lobe is a little bit bigger than the previous one. Now that's because we have that spherical orbital spread out over only 2 of those p orbitals, to getting us 3 equivalent orbitals. So it's going to be a little more S-like. So it's going to be a little bit rounder. So that's why the orbital is listed here as showing you that it's bigger. Now, when we fit those together, this tiny little lobe kind of squeezes in between the 2 others, and the big lobe is there. That's how we get our trigonal planar look to it. But remember, we still have 1 unhybridized p orbital. So I'm going to highlight that right here. The unhybridized p orbital is the one that sticks above and below that plane made by those 3 equivalent p orbitals. So these are the 3 equivalent that make that trigonal planar. And so these are the center of it, and that p is above and below the plane made by those 3 orbitals. So because it's above and below, we can do our direct bonding with each of these. Then we have to do our overlap bonding with the 2 halves of the p. And you'll see that again in a little bit. All right, so we've only used 2 of the p orbitals and the s, so we have a bigger lobe. It's more uneven than it was before. Okay, so now that we have that p orbital above and below that plane, that's where we get to do that next bonding, that overlap bonding. Okay? And so we'll take the things that are trigonal planar here in this plane, we're going to leave them there. And then we're going to take these 2 unhybridized p's. There's one on one carbon here, and then there's another one on this carbon here. And instead of actually bending them, what we're going to do is we're actually just going to share electron density above and below this point. Okay. Each of those p orbitals typically has 1 electron in it. So you have a 1 electron over here, 1 electron right here, and that electron's partially shared above and below that plane. And so what would it look like on the side with a little structure here is if we look at this diagram down here, we have our direct bond here between the 2 carbons. Notice that those electrons are held right in between the 2 nuclei of those carbons. Then we have the overlap above and below that plane. So 1/2 of the electron density is here, and 1/2 of the electron density is above. That gives rise to that planar molecule, but it also gives rise to what we call our pi bond, or our double bond. Okay. And it doesn't have to do just between carbon. The oxygen that we bond to it, if we double bond an oxygen to the carbon in a carbonyl compound, is also sp2 hybridized, meaning it has 3 equivalent sp2 orbitals that bond, or in the case of oxygen, holds our lone pair here and here. So these are lone pairs in that plane. And we have that unhybridized p. Now that unhybridized p is going to be above and below that plane so they can overlap. So we'll get a direct sigma bond. The first bond is our direct sigma bond between the carbon and the oxygen. And the remaining electrons are shared above and below that plane to give us our pi bond. But that shows us that not only is the carbon sp2 hybridized, but the oxygen is sp2 hybridized as well. Okay, so the last of the hybridization ones is what we call sp. In sp, you have the spherical orbital in one of the dumbbells, leaving the other two dumbbells untouched. Okay, so in the case of that, we have one of the sides being very big and spherical, and when we try to get the other one next to it, that's where we get the linear configuration that we see with just those direct orbitals that can do our overlap. And then we have two untouched P's. Now, remember, when we first did them, one was in X and one was in Y and one was in Z, right? So we still have one in X and one in Y, and our new hybrid orbitals are the ones in the other axis. So they're spread out as far as they can be at that 90 degrees, but because those are electronic above and below, our actual bonding is going to be at 180 degrees, a linear. Okay. So how do we use that to make a double bond? Well, because the SPs are hybridized and are in this single, line here, it's linear here, and we have one p orbital that's in this X plane, the one that's in that plane can overlap with the other one that's in that plane, forming one of our overlap bonds, one of our pi bonds, okay? And these are wrong, these symbols are wrong. These should be pi bonds, and it should be a sigma bond here in the middle. Okay, so only these two pi's, these two p orbitals that are in the same plane can bond together. And so they bond to form one pi bond. Now, the other orbitals that are on this other axis now, because they all look like each other, they can bond to each other, forming our second pi bond. And let me go ahead and show our sigma bond, our linear sigma bond, oops, as this blue one here, okay? And our ones that are in the x-axis, or in the plane right here, form our one pi bond. And the ones that are sticking above and below the plane form our second pi bond. So when we have a triple bond, we have one sigma bond, one pi bond created by two p orbitals in one plane, and one pi orbital bonded in the other plane. So we have X, Y, and Z all taken care of in our triple bond. Okay, where are we at? 145. Let's talk some. Actually, pretty close enough. Okay. So, to kind of summarize the idea of where we see carbon bonding in these different ways, if we have four groups bonded to carbon, that means we must have an sp3 hybridized carbon. Okay. So when we try to look at their predicted angles, they're going to be close to this 109 degrees. My wife will have to get that. When we have 3 bonds to carbon, we know it has to be sp2 hybridized, okay? And when we have those 3 different groups bonded to carbon, it has to be that sp2 hybridized, and we can get to that 120 degree trigonal planar for the sp2 hybridized, but then the p orbital is up outside of that plane, in the z or the x-axis to that plane. And if we're only bonded twice, we have the linear forms the one axis, and then the pi bond is going to be in one direction, and the other pi bond is going to be in the other direction. Okay. So I think that'll get us to where we need to be today. We're right at about 1:45, and that's about when class dismisses. So what I'd like to do now is I'm going to go ahead and stop here, and ask if anybody has any questions about the shapes of these molecules and which orbitals contribute to which kinds of bonds.
Dr. David.
Yes.
Oh, I mean, I wrote it down, so obviously it's probably pretty important because you said it a few times. But like the sp3 relates to the 4 sigmas, the sp2 is a 3 sigma 1 pi, and then sp is 2 sigma 2 pi.
A sigma on each side of of the central atom, and then 2 pi or 2 pi's. Yes.
Yes, sir. Thank you.
Could you scroll up again really quick so that I can write down? Yeah, perfect. Thank you.
Okay. So again, this is table 1.8 in the book. So if you have a digital or electronic copy, this is also there as well. But it's always a good idea to give a little bit of practice by writing it in notes as well. So 4 bonds, think of it as S has a 1 on it. So sp3 is a total of 4 orbitals to bond equally. The 3, sp2, S has 1 and a p has 2, so that's 3 equal orbitals. And the sph gives us 2 equal orbitals. So that's one way to help remember as well. Okay, and it's really kind of, important to kind of put this into your, vocabulary, because when we go for functional group transformation, what we'll see is sometimes we go from an sp3 hybridized carbon to an sp2 hybridized carbon, or we go from an sp2 hybridized carbon to an sp3 hybridized carbon. And sometimes we stay in the same hybridization. And so I might throw out, a thing saying, oh, we're going from an sp3 hybridized carbon to an sp2 hybridized carbon. And then immediately you should say, okay, well, that means we're going to change the shape of the molecule because those give us different shapes. Okay? All right, if nobody has any more questions, I'm going to go ahead and stop recording and stop sharing. And if you want to hang out and ask a question, I can do that. So stop recording.